Hey everyone, this is Scott from RedmondPhysicsTutoring.com, and in this video I'm going to go through a really tricky example where we have capacitors charging in series and one of the capacitors has an initial charge. This was inspired by a problem that one of my tutoring students brought to me, and we didn't really like the way it was explained by the official textbook solution. So I'm going to go through a problem that's very similar, different numbers, and try to explain it in a way that makes a bit more sense. So we start out with this circuit that has two capacitors, an EMF, and a switch. And we're given that the C1, capacitor 1, has capacitance of 10 microfarads, C2 has 30 microfarads, the EMF is 40 volts, and we're told that the first capacitor is initially uncharged. C2 has been initially charged to 10 volts. So this means that it was connected before setting up in this circuit. It was connected to a 10 volt battery and allowed to fully charge until the voltage across C2 was 10 volts. Now, the problem that we have to solve is to find the potential difference across C1, so delta V1, and to find delta V2, the potential difference across C2, after the switch is closed. So given that the second capacitor, C2, was initially connected to a 10 volt battery, we can actually find the charge on that capacitor before the switch is closed in the main circuit. We know that the charge on the capacitor is the capacitance times the voltage, so we have Q equals C times delta V. We can put in our 30 microfarads for the capacitance, 10 volts, and we end up finding out that the initial charge is 300 microcoulombs. Okay. Q1 is 0, Q2 is 300 microcoulombs, and now we're going to close the switch and see what happens. And this is the really tricky thing. When the switch is closed, the EMF sets up an electric field in the circuit that takes electrons from the left plate of C1 and places them on the lower plate of C2. And I'm trying to illustrate this with an animation. This makes the left plate of C1 positive because we took an electron away, and it makes the lower plate of C2 more negative. Now, C2 was initially charged, and the lower plate here is the negative one. This is how the problem was set up. So the EMF has actually added another electron there. This extra electron at C2's lower plate repels an electron from the upper plate, so it makes C2's upper plate more positive than it was, and that electron moves to C1, where it is attracted to the left plate. Now, it can't go through the capacitor because there's an insulation in between the two plates, so it sticks to the right plate of C1. Okay, this process continues, and I'm showing it with one electron at a time, but in reality it happens almost instantaneously with many electrons. The important thing to notice is that C2 always has 300 microcoulombs more charge than C1. So this gives us a really important clue to solving the problem. We can express this algebraically as Q2 is equal to Q1 plus the 300 microcoulombs that we solved for initially. Now, the EMF will continue driving a current until the total voltage across both capacitors is equal to the EMF at 40 volts. And we can express this algebraically as EMF is equal to delta V1 plus delta V2. Now, knowing that Q equals C delta V, we can express delta V as Q over C. And substitute into this equation, we get the EMF is Q1F over C1 plus Q2F over C2. We know the EMF value, we know C1, we know C2, so we have two unknowns. But we also have another equation that we just set up, knowing that Q2 has 300 microcoulombs more charge than Q1. So we can substitute that into the equation, and after that it's quote-unquote just math. So we're doing the algebra now to solve for Q1 final, and I'll speed up the video at this point. So we find out that Q1 final is 225 microcoulombs. We can substitute that value back in to solve for Q2 final, and we get 525 microcoulombs. And once we have those values, we can find the potential difference across each capacitor, which works out to 22.5 volts across C1 and 17.5 volts across C2. Thank you so much for watching this. I really hope that it can help you, and I appreciate the time that you take out of your day to watch something like this. If you do find it helpful, please leave a note in the comments on YouTube or head on over to my blog at RedmondPhysicsTutoring.com, and you can also leave a comment there. Thanks again, and good luck.